There are multiple aspects which are critical in industrial applications, being one of them achieving very high reliability at the same time as maintaining low latency. You can imagine a scenario where there is an autonomous vehicle moving around the factory floor and how critical is to maintain the connectivity in order to avoid accidents that could halt the production. In a factory environment, there could be multiple types of obstacles, including things like a metallic wall, very high dimension robots, or moving objects, which could potentially reduce the quality of the signal received, which could lead to such failures. In order to cope with these kind of situations, the 3GPP has specified a set of ultra-reliable features as part of the Release 16. PDCP duplication is one of them, which natively adds support for multi-connectivity in the 5G link. PDCP duplication helps improve reliability by increasing the redundancy, which is done by sending the same PDCP packet over multiple paths at the same time. In this example, the robot is moving along the factory and connected to 5G NRDC to two different nodes. At a certain point, the signal coming from the first 5G node is blocked, which causes few critical PDCP packets being lost due to high packet error rate. However, thanks to using the redundancy of packet duplication, those critical packets can reach the endpoint without impacting the latency. Let's see now an example and how easily we can debug issues using the Keysight WaveJudge Signal Analyzer.
I am now going to show how the WaveJudge can test private networks. If we look at how this is set up here, we have a UE that's simultaneously connected to two different base stations. So one base station which is in the sub 6 GHz band, and one base station which is in the millimeter wave FR2 band. And so the UE can be connected to both simultaneously. This is called dual connectivity. And so we see here, for example, we have a capture that was performed with the WaveJudge and analyzed. We see that it has two cell IDs, so cell ID 0 for the sub 6 GHz band and cell ID 1 for the millimeter wave band. And here we have what is listed here is the result of the analysis of this capture. So we can select what we want to see in this capture. So first I will only show the layer 2 messages to make it a little clearer. So for example, here we have a PDCP message preceded by a RLC message that came from a MAC message. So we can double click on each of those messages to see their content. So here is my RLC message, and if I double click the PDCP inside the RLC, now I have the PDCP message that is carrying IP data. I can also double click on this IP data, and what this is going to show is the headers of the IP and UDP data inside this PDCP. So this is what makes the layer 2 of 5G NR, those three sublayers, MAC, RLC, and PDCP. Now, if I show only the PDCP sublayer, what we're going to see here is we have PDCP messages from cell ID 2 and 0, which are more or less interleaved. And I can double click on two of them. And by doing so, what we see is that we can compare the content on both. And the first thing we notice is the sequence number is identical, and we can actually look at the data in the hexadecimal panel below, and we can see the data looks very much alike. We can actually double click on those IP packets as well, which can also help to compare. We can compare the headers, verify they are identical as the data. So they are actually identical. The PDCP PDUs are identical, and this is highlighting this PDCP duplication feature. This is exactly what the PDCP duplication does. It allows PDUs to be sent in a parallel fashion on two separate connections to two separate nodes, basically a master node and a secondary node, which are in this case even in different bands, in an FR1 band and FR2 band. So that really provides a lot of redundancy and diversity. So the WaveJudge can help analyze this in great detail. So I showed how we can analyze in detail in layer 2. By enabling the file layer messages, what that allows us to do is to look at the physical characteristics of the MAC messages. So let's suppose, for example, that one of these PDCP sequence numbers was missing for one of the two paths, and we would like to understand why, what happened there. So what we can do is we can look at the underlying PDSCH, and now so this PDSCH, for example, was received on cell ID 2, and now if we set, for example, the constellation to cell 2, we can see its constellation. We can also visualize it in time domain, and we can see it in frequency domain, for example, right here. And the most important view, most interesting usually, is this view, which is two-dimensional power, which is both in time and frequency. That's why we call it two-dimensional. And in here, really, we can compare the scheduled resource elements versus the ones that were energized and make sure that they do match. So, for example, if I unselect PDSCH, now I see the received energy, whereas when it's selected, the color coding is indicating actually where the PDSCH was scheduled, as well as the DMRS. So the DMRS symbols are shown in a lighter color, lighter green than the data resource elements. And so you can, with this view, you can zoom in even more, and you can make sure that what is scheduled is actually what was received. So that's an example of issue that becomes easy to troubleshoot, an issue where those would not match. So what's scheduled and what's received does not match. It's something that we can easily troubleshoot this way. So what I have shown here is the feature of PDCP duplication, how it can be visualized at multiple layers, from the file layer to even IP layer. And this PDCP duplication is a key feature to achieve URLLC, ultra reliable low latency communication, which is important for many private networks.